Yeah, thank you all for giving me time to be here. And today I want to introduce one of our newly developed toolkit, OxonFair. It is a flexible toolkit for algorithmic fairness. So this work is done with Owen, me, and Sandra, Brent, Chris in Oxford Internet Institute in the University of Oxford. So currently we have seen many prediction methods in biomedical to predict some result, but we want to claim that there are maybe some bias or unfairness in such kind of prediction. So why we develop this tool? We want to solve this problem. We not only resolve the bias in the prediction, but we also want to improve the accuracy by remove the bias. So this is our tool. So generally, it is a Python-based toolkit to measuring and enforcing algorithm fairness with focus on high-capacity model. So by high-capacity model, I mean some models that are very easy to overfit to the dataset. So nowadays, we use very large models, like language models, have billions of parameters. Usually, it is overfitting. So this kind of tool is just designed for such kind of task. So we can solve the problems in computer vision, natural language processing. We can also support the capital data, which are three main kind of data types. Our tool is very expressive than existing toolkits we will compare later. And we hope this tool can be suitable for applied data scientists and practitioners. So why we develop this tool? So here are some motivation of this tool. You can see this is a news report saying that in AI skin cancer diagnosis, generally you use some AI tools to detect this image. It usually has some bias on the people with black or dark skin. Similar situation happens during the COVID period. So some tools, equipment for COVID detection may also have racially bias in such kind of scenarios. Here is another example, not in biomedical, but in A-level testing score prediction. So some report also shows that this kind of report also have some bias. So generally, if you use machine learning to do some prediction based on some real data, it may have some bias. So this is why we designed this tool. We hope this tool is a harms-first design focus with OxonFair. By this, we mean we hope our tool can leveling up the disadvantaged group, not only make it fair or remove the bias. We also want to improve the accuracy scores. So this is a very challenging task. Generally, a lot of things will cause our machine learning model to be biased. There are some sources from that can introduce some bias into our models. The first one, or I think is the biggest one, is the data imbalance across subgroups. So this is often happens if we use some real-world data. For example, currently we are doing some experiment on the biobank data, mainly from the UK. So because all of the data collect the people's data from the UK, it usually happens to have a lot of white people's data, but it lacks people from African or from Asia. So this is where the bias come from. If you train the machine learning model with this kind of data, the model itself will have some bias. The next one is the class imbalance. By this, we mean for some diseases, you can only have maybe few samples, less than 10 samples in your algorithm or in your data set. So your model, the prediction of your machine learning model will be very random and unpredictable because it does not have such kind of data. There are some other kind of bias, resources of bias, like spurious correlation. So here is an example. You can see this is a skin picture. We are trying to use some algorithm to detect some diseases, but we have some lines, human annotated lines. But if we train the machine with this image, machine will think that this kind of lines are the most important feature to predict these diseases, which is also undesired. There are some other sources like label noise. So this is also very commonly happens if we ask annotators to annotate the data. They often make mistakes. This is unavoidable. And also there's another reason that inherent characteristics. So for some patients in some subgroups, they may not like to do some detections or data collections. So we do not have enough data in this particularly subgroup. So this can also lead to some bias and unfairness. So to solve this problem, and currently there are many researchers trying to solve this problem. Generally, we categorize this kind of methods into three categories: the pre-processing, in-processing, and post-processing. The pre-processing is very easy, right? The main bias come from the data. So we should make a better data. We just ask a lot of people to help to make the data as good as possible. So this is very straightforward. The second one, in-processing, is machine learning people like me, like most. You just design a very fancy machine learning models by adding some fairness rules into your model and just train the model with the data. The last one is currently we are doing in this road is the post-processing, which means we just debias after we already trained the model. A very interesting question is, does the in-processing work? Because a lot of machine learning people like me like to develop such kind of model. But some researchers last year developed a benchmark called MedFair. So they collect a lot of algorithms and a lot of the data. They run the algorithms on this data, and generally they find that the state-of-the-art method does not outperform a model that doesn't consider fairness, which is very upsetting. So this is why we want to use the post-processing, which means we will handle the fairness after we already trained the model. So because generally you're training a fair model doesn't mean that they are fair during the validation or testing time, because there are a lot of kind of definition of fairness. So maybe during the training phase, we can only use one definition of the fairness, but in the testing time, we are using another definition of fairness. So the in-processing model may not work, but the post-processing can help this kind of tasks. And this is why we design our OxonFair as a post-processing style. Another advantage of this kind of design is that we can take advantage of a lot of backbone models. You know, currently we have a lot of pre-trained model like Llama and some other BERT models. We cannot train these models by ourselves, but we can post-process with the fairness with this kind of very large backbone models. So based on this idea, a lot of companies developed a lot of toolkits. These are some toolkits that are very famous. The first one is the FairNum, developed by Microsoft. And IBM also developed their fairness toolkits. Currently, this kind of toolkits have some issues. The first issue is they do not support models overfit to training data. So we have just mentioned this. And they do not provide the support for computer vision and NLP, so limited the application scenario. And also this model has some limited expressiveness, so the fairness score are very limited. So this is another paper from our previous research. We claim that fairness and the performance measure are context dependent. So for example, in medical usage, or in education usage, the definition of fairness should be different. So we hope our model can support as more fairness definition as possible. So here is our contribution beyond existing toolkits. Our toolkits support NLP and computer vision currently can help a lot in medical usage. And we support and we are very robust to a wide range of overfitting challenges. So if you have a very large model, our model can help with this. and we are more expressive. We support 14 fairness metrics, and we do not require protected attribute information and testing time. Here is a detailed comparison. You can see that for the fairness definition here, we support more than 14 fairness definition, which means we can support more scenarios. And you can see last 3 lines, we support the tabular data, we support computer vision, and the NLP data, which make our toolkit applicable in more scenarios. Here's how the OxonFair works. So we hope we can make this tool in 2 lines of code. The first line, you just throw your classifier, your validation date, and your group information into the predictor. So this is the validation set. And then you apply the model on the testing set or the application scenario. You can see the last line is how you call this fairness predictor. You can see, so this line means we want to improve the accuracy, but we want to control the fairness score of equal opportunity to 0.01. Here is how we can apply the OxonFair tool on the deep learning models. So in the deep learning models, generally we have one hit predictor for the log loss just for your specific task. And we have another squared loss for the group predictor. So you just predict the ethnicity information of this data point. And our toolkit can find the best most suitable lambda to combine these 2 hits together. So this figure shows how our models works. Here's the example shows that our model can achieve the best Pareto frontier compared with some existing tools. We focus on leveling up the scores by our tool. So you can also use the fair predictor like this. The last line is the code. You want to improve the accuracy, and you hope that the minimal recall is around about 0.7. So you can fix one score and to maximize the other score. Here are some experimental results for computer vision. So here we want to detect the blonde hair person in an image. So you can see our OxonFair tool achieves the best Pareto frontier. So if you fix the fairness score, the X-axis, our model can achieve the best Y scores. While you want to fix the accuracy score, generally our model can have the best equal opportunity scores. Here are some experiments on NLP data. So this is Google Jigsaw data. So this task is just hate speech detection, which shows that our model is capable to be applied in many scenarios. We provide a lot of notebook in our repo, and you can see we provide this kind of examples. So I guess maybe some of the example may be quite similar to the scenarios you want to use. So here are the scenarios that OxonFair can help. So if you have a task in computer vision or natural language processing, you can choose the OxonFair because it supports these 2 tasks. And if you have multiple protected groups like ethnicity, our tool can also help. So for some other tools, maybe some only support two groups like gender, but our tool can support something like ethnicity. You can have many groups here. The next scenarios is if you do not have knowledge about the protected group at the testing time, which means when we apply our tool in practice, you do not need to give the group information for the data point. So you can just give some raw text or image. You do not have to give the information of which gender or which ethnicity this figure is belong to. So this is a very big advantage. The other scenario is that if you want to be flexible in your choice of performance and the fairness metrics. So as I just said, we support more than 14 fairness metrics. So I believe one metric may fit for your task. And the other scenario, if you want to set minimal acceptable harm thresholds for leveling up, which I have shown in the code, just the 2 lines of code can help to improve the performance and reduce the bias. And the last scenario is when you care about the minimax fairness, utility optimization, and the conditional fairness measure. You can also try this tool. And our tool is already on the pipe install, so you can just use a single line of this code to install our tool to your machine. And you can scan the QR code for this is our GitHub repo, and that is for our paper. And if you have any question, you can ask me or write email to our group. Thank you very much.